Yeah, no, it's like 4 or 5 people. You go by the line, we have this. When I could see more, it's always. Yeah. Very low now. nicer. Or a computer actually works. I don't know what the problem is, like, it's either one from the submarine probably. It's almost 5 minutes.
Hey, good. How are you?
Too bad. We'll just try and knock out some homework.
It's a lot.
Yeah. 4 problems, and then I saw, oh, okay.
The 4 problems is misleading. There's always parts A, B, C.
All the way to today.
Yep.
Dude, I just would be, they got some everything, so I couldn't go. And that will ask and then. I love that. You think that, I will say. I think we are really not because it's sexually one of those two section could be like yeah. My group is the Venus but I think it's like yeah. I love
Sir. I haven't seen. I don't know.
Dude, I like had the homework. Like 11. And then my just take a picture, put it on the Google Doc, and then like down the doc and PDFs. My hair was yeah. As I submitted later, it's like no, they didn't say anything.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good. Good to hear. I had a little bit of a rough weekend. So on Friday, I committed a cardinal sin that no son should ever do. I forgot my mom's birthday. Yeah, I know. The funny thing is my dad actually gave me an out, so he calls me, and which is not unusual because my dad calls me a lot just because him and my mom, they want to talk to their grandson. And then my dad was like, "Oh, does Isaac want to say happy birthday to grandma?" And then I should have just played it off like, "Oh, happy birthday," but I gave the worst reaction. I'm like, "Oh yeah, it's mom's birthday today." So my mom was pissed at me the whole weekend. And then yesterday, I also forgot that it was my wedding anniversary with my wife. But it's okay. My wife forgot too. So, I was actually the first one to remember because I brought home flowers. But I got home, she's like, "Oh yeah, it's our wedding anniversary." So yeah, it's when you have a kid, it's things slip through the cracks a little bit. But so my wife is happy, mom is not happy. So we'll work on that. Okay. All right. So plan for today is we are kind of right in the middle of our discussion on second order differential equations. So we'll continue with that discussion. So I'm hoping to get through at least start the non-homogeneous part today. I'm guessing, you know, in 250B, you guys learned multiple different methods to solve for non-homogeneous solutions. We're only going to use one in this class just because of time. We're only going to go over undetermined coefficients. But that's more than enough to kind of do what we need to do. Okay. All right. So announcements. Homework 2, I posted just this afternoon. I apologize for getting up late. I was very forgetful over the weekend, as you might have seen. So the due date for that is going to be next Friday, which unfortunately is Friday the 13th, but you know, that's not going to affect the grading. Okay. So I haven't looked at your homework ones yet, so I'm probably going to start grading those tomorrow. Usually I'd like to grade stuff within a week after it's turned in. So you know, latest I'll have those graded is by Friday. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. All right. So where we left off last week was the application of second order ordinary differential equations with constant coefficients to the mass spring damper. Right. Quite a mouthful. So we're just going to call this mass spring dampers. Okay. So the system that we were looking at, a little bit contrived, but you know, this you can, like we kind of discussed last time, you can apply mass spring dampers to all different kinds of engineering systems. You'd be surprised at, you know, how many engineering systems can be applied to this kind of simple analogy here, right? So we have a spring, we have a mass, and we have the damper, which we're kind of modeling as kind of like a water resistant sort of thing, right? Okay. Right, so 3-component system. And then what we saw last time is you know, if we applied you know, very straightforward kind of you know, laws of physics here, things like Hooke's law, you know, formula for air resistance, we can come up with a second order differential equation that models this behavior. Okay? All right, and so that differential equation is m d squared x dt squared plus b dx dt plus kx is equal to 0, okay? Where our dependent variable x here, x is the displacement of the mass, okay? Okay. All right, so generally what we expect, so if you have a system like this, and you take your mass, you can displace it, right? So you can basically just kind of take your hand and kind of move the mass over to the right, right? Right, and that's going to be your displacement x, okay? All right. So today, you know, what we're going to start with today is we're going to look at this differential equation. We're going to look at the typical solutions to this differential equation. So remember last time we talked about there's typically 3 different cases for when you're solving second order ordinary differential equations with constant coefficients, right? We'll talk about what those mean physically for these types of systems, and then, you know, we'll do kind of an example applying all this together. Okay. All right, but that's just kind of a quick recap from last time. Very, very quick, just a couple minutes. Any questions on just this concept here? Okay. All right. So before we get into the solutions, you know, let's talk a little bit about you know, how we model this system, okay? Or how this system is used in practice. Okay. Okay. So like we said last time, so you know, because of the spring, you know, generally what's expected is that, you know, if you were to displace the system, if you were to kind of disturb it, move the mass away from its equilibrium position, the spring is going to want to bring it back to its original position. Right. So typically, you know, in terms of physics and in terms of engineering, what we say is that the spring applies a restoring force. Okay? Okay. Right. And so a lot of times, when we're looking at mass spring damper systems, we're usually very interested to see how our physical system, how it's going to behave, if we were to introduce some kind of disturbance or any kind of perturbation. Okay. Okay. Now, the answer to that question, depends on the relative magnitudes of the physical parameters of the system, right? So it depends on how much mass you have in the system, depends on how much stiffness you have in the system. That's your spring constant K. And of course, it depends on how much damping you have in your system. Okay. But for the sake of our argument here, we're going to say that there are generally two types of disturbances that can occur in these mass spring damper systems. Okay, so the first type of disturbance is what we typically call an initial displacement. Okay. So those are situations where, your mass or your system is forcibly kind of moved away from the equilibrium position and then released. And then, we can kind of observe how the system kind of comes back to its equilibrium position. Okay. Okay. So mathematically, we often describe an initial displacement using some kind of initial condition, right? And in terms of how that's done, it's just like the name implies, initial displacement is an initial value on the value of x. Okay? So for example, you might see this as like x of 0 is equal to, I don't know, x naught, okay? Where x naught is just some number. And that x naught there represents our initial displacement. The second type of disturbance that we often will see is some kind of what we call initial velocity. Right. So with an initial velocity, the mass starts with some kind of speed. It's either moving forward or back or up and down. Okay. Okay. But that initial speed is not sustained, or it's not it's not some external force that's being applied continuously. It's applied right at the beginning and then released. Now, because of the actions of the spring and the damper, that initial speed will persist a little bit, right? So just because we're not forcibly giving it more speed as time goes on, its effect will persist, right? So initial velocities, these are usually used to represent cases where maybe some object impacts our mass very quickly and then leaves. Okay. And so kind of the general term that we usually call for this, at least in mechanical engineering, is some kind of hammer blow condition. Okay. Because if you think about it, if you have an object and you impact it, right? And so you just like you take an object and you just hit it, right? Then the time that your fist or whatever is impacting the object is only very brief. Okay. And mathematically, the way that we do this is we give some kind of initial condition on the derivative of x. And so we have dx dt at x is equal to 0 is equal to v naught. Okay. Should be dx dt. I'm sorry, not dx dx. That makes no sense. Okay. And so as we kind of go through the three different, the three different solution types, kind of keep these in mind and kind of think about how, the different solution types respond to these types of disturbances. Okay. All right. Any questions on this so far? Okay. All right, so let's go through the three different types of solution. And so, this is going to correspond to the three different types that we went over last Wednesday. The only difference is now is that, we're giving names to these three cases. Okay. Okay. So remember, case one. Case one was a situation where our characteristic polynomial gives us two distinct real roots. Okay. All right, so if you recall from last time, in this situation, our solution here is going to be a summation or linear combination of two decaying exponentials. We have x of t is equal to c1 e to the minus lambda 1 t plus c2 e to the minus lambda 2 t. Okay. And remember, like we said last time, that when you're modeling physical systems, and your differential equation is comprised of these kind of physical properties like mass, spring constant, those are always going to be positive. And so when you have, positive physical quantities, your roots of the characteristic equation, at least the real part, is always going to be negative. So that's why I put that negative in there. So negative lambda 1 t, negative lambda 2 t. Okay. Okay. So what does this look like? So if we were to graph this, right, we know what the graph of a decaying exponential looks like. Right. So let's assume for this case that we just have an initial displacement, so no initial velocity. Okay. So if our mass here were to start with an initial displacement, in this case, our position will decay down to 0, just like that. Okay? So that's t x of t. Okay. And so because of this, because we have, our disturbance here is essentially just decayed out over time, we call this the overdamped case. So the situation where we have two distinct real roots, you get a decaying exponential, or two different decaying exponentials, you get an overdamped solution. Okay. Now it gets this name because, oftentimes you see this type of solution when the damping in your system is very powerful. So the damping kind of overpowers any kind of spring constant, any kind of mass that you have in the system. Okay. Now, what's interesting here is that, you have two different decaying exponentials and, in general, they have the same shape, but they are different, right? And so, what you actually observe, right? Generally, what you actually observe here is the plot of the curve with the smaller lambda value. Okay. And when I say lower lambda value, I mean the one that's lower magnitude. So let me actually change that. Okay. So let's say, for example, that, you solve an overdamped solution, you get lambda 1 is equal to -1. lambda 2 is equal to -3. Okay. Right. And if you were to plot the solution as a function of time, generally you're gonna observe the solution for lambda 1 is equal to -1, just because that one has less magnitude. Okay, so that one decays more slowly than lambda 2. Okay. Okay. Now, this kind of feels like we're splitting hairs because, oftentimes there's not that big a difference between the lambdas. And so, eventually they're all going to go down to 0 anyway, right? And so, the fact that one is decaying less quickly is usually kind of a moot point. But when you compare this to our next case, this is actually pretty important, okay? Because what can happen with overdamped systems, oftentimes, you apply damping because you want to take the disturbances, you want to damp them down to 0. Okay. Actually applying too much damping can actually hinder that process. Or in other words, you're not going to get as quick a damping, if you apply too much damping. Okay. That was kind of a tongue twister, but let me kind of put that in words, right? So if you apply too much damping, it can actually take a while for your solution to come back down to its equilibrium position. So that's really important because, there are a lot of engineering systems where you want to apply damping, but you don't want to apply too much. Okay? So for example, the example that we're going to do later is like the shock absorbers in your car, right? So generally you want to damp those out, right? You run over a pothole, you don't want to be, on a low rider kind of bouncing up and down forever, right? But you don't want it to be, you don't want it to have too much damping, because if you have too much damping, you run over the pothole, your car will spring up and then it'll just very, very slowly come down, right? You want it to kind of come up and then come down and then kind of just stay there, right? So you have to be careful with the damping. You can kind of go a little bit too crazy. Okay. All right. Any questions on over damping? Sorry. Okay. All right. So let's go over the next case. All right. So if you recall from last Wednesday, the second case that we went over was when we had a repeated root. Okay. Where essentially, we had two roots that were the same, or our quadratic equation gave us two roots, right? And if you recall what our solution looked like in this case, x of t, right? We had c1 e to the minus lambda t, right? So that was one root. And our second solution was the same exponential, but we multiplied by t in front. So we have c2t e to the minus lambda t. Okay. Okay, so let's draw what that looks like. Okay, so once again, I'm going to take a situation where we have just an initial displacement, but no initial velocity, just to kind of keep it simple. Okay. Now, this one's interesting because, we do have a part of the solution where, we have t. So there's going to be a brief part of the solution where you move the mass away. It's actually might start to go up a little bit. Okay. So it actually gets further away from the equilibrium, but then, that doesn't last for long, because the solution then comes right back down because the decaying exponential kind of eventually takes over. Okay. All right. And so if you compare the plot of the repeated root compared to our overdamping, they look very similar, right? So this part at the beginning usually is no big deal. So usually we don't really care about that too much, okay? Now, the interesting thing about this, and it's really hard to kind of illustrate, with a pencil and paper like this, but with overdamping, you actually get a decay back down to 0 in the fastest way possible. This decays faster than overdamping. Yes. Mhm. Okay. And so if I were to overlay, a similar system, so, if I were to overlay like an overdamped system on top of this, it would look kind of something like this. So we start from the same position here, right? And it would kind of look something like that. Sometimes it's not this pronounced, I'm kind of exaggerating it a little bit just for the sake of here. But this shows you that, in general, critically damped systems will decay much faster. Okay. And why is that, right? So the fact that we have a single root here means that, our two decaying exponentials are going to decay at the same rate. Okay. Right. So you don't have a situation like you have in overdamping, where you have one that's decaying very quickly and one that's decaying slowly. The two decaying exponentials in this case are kind of more or less very balanced, right? And the effect of the linear term, the effect of the t, doesn't really make too much of an impact on the result. Okay. And so because of this, we call these types of systems critically damped. Right. And so if you have an engineering system where you want to kind of decay or damp out these disturbances as fast as possible, you want to be as close to critically damped as possible. So you want to kind of tweak, you want to tweak the settings, tweak the stiffness, you want to tweak the damping such that you're close to critically damped. Okay. Usually you don't want to be right at critically damped because you're right kind of on that precipice. And so technically you want to be over damped, but you want to be more critically damped than over damped, if that makes sense. Okay. It's a spectrum, and you want to be closest to critically damped as much as possible. Okay. All right. Any questions on critical damping? Critically damped. Okay. All right. So then let's go through the last case. Okay. Probably the most interesting one. So case 3 is the situation where we had complex conjugate roots. Okay. And so if you remember, our solution looks like the following. So if x of t is equal to e to the minus alpha t multiplied by a cosine omega naught t plus b sine omega naught t. Okay. So remember, this was our decaying exponential that we talked about last time, but we have, or decaying sinusoid, excuse me. So we have kind of oscillations that come with the sine and cosine, but the magnitude of those oscillations are going to go down with time because of the because of the exponential in front. Okay. And so if we draw this out, we kind of already discussed this last time, so it's going to go kind of quickly, right? It kind of looks like the following, where, you have oscillations that, maybe look like this, but eventually those oscillations are going to damp down. Okay. So in all three cases, as long as damping is present in your system, your mass is going to return back to its equilibrium position. That's a given. It's just, how it gets there is kind of the, kind of the question, okay? So this situation, because we have an oscillating solution, we often call this damped oscillations. Okay? Or in other words, or another way that we often call it is underdamped. So in other words, there's not enough damping or there's not enough friction in the system. So, the system is allowed to kind of oscillate and fight. Okay. Okay. So last time, we spent quite a bit of time talking about these, and so, I don't want to say too much more. So next thing I have is an example, but any questions on this before we jump into the example? Okay. All right. So let's do an example. Okay, so like I mentioned before that, one of the most common applications for second order ODEs and mass spring dampers is in automotive suspension systems. Okay, so let's take a look. So we're just going to look at one of the wheels here, right? So this block, we'll say that this is the part that connects to your car. Okay. Okay. And so generally, as your wheel attaches to the car, I know this is I know it's not this simple, but just for the sake of argument, right? Usually there's a suspension system that's connected to the car, right? So the suspension system oftentimes consists of a spring, there's a damping component, right? And then this connects to your wheel. Okay. Right, so these two parts right here, this is your suspension. Right? And the wheel in this case, we're going to treat the wheel as the mass. Okay. So we have a very classic kind of mass spring damper. So, we're going to assume that all the values for the parameters are known, okay? In fact, we can kind of just give values for these. So let's assume that the mass, at least for now, is going to be 12-pound mass, okay? The damping constant B, we're going to assume is 240. Okay. So typical units for that is, let's see, pound per feet per second on top. Okay. And the spring constant K in this case is 1152 pound per feet in this case. Okay. So we're going to take these numbers, we're going to take this system, and we want to basically analyze its behavior. All right. Right, so when I say model, basically we're going to solve the differential equation. We're going to classify the solution, right? So we're going to classify our solution as either being overdamped, critically damped, or underdamped. Okay. We're going to solve it for, a certain kind of a disturbance, and then, we can see what we obtain from this. Okay. Okay, so let me go ahead and actually write out all those steps. So part A here, let's write out the governing differential equation. Part B, we're going to solve for the general solution. Okay. Part C, we're going to characterize it. right? And then part D, we're going to solve for the case when the speed runs over a speed bump. Okay. All right, and we'll talk more about that kind of once we get down. Okay, so let's start with part A. So part A is pretty simple. So we have our, second order ordinary differential equation with constant coefficients. All we got to do is just plug in the coefficients here. Okay. So part A, we have our differential equation m d squared x dt squared plus b dx dt plus kx is equal to 0. Okay. So let's just go ahead and plug in the numbers. And so all these numbers are consistent with each other, so we don't have to do any conversions. Okay. So we have 12 d squared x dt squared plus 240 dx dt plus 1152 x is equal to 0. Okay. All right, pretty straightforward, pretty easy. Part B. So part B, we're going to take this differential equation and we're going to solve for the solution. Okay. So this part is pretty straightforward too. So we just have to find the roots of the characteristic equation. But one thing we'll do first is that, we'll put this equation in standard form. Okay. So remember what standard form means. So standard form means that we take the highest order derivative and we divide by its coefficient so that it has a coefficient of 1. Okay. So in this case, our highest order derivative is the second one. So we're going to take every term and divide it by 12. Okay. And so we do that, we get d squared x dt squared. 240 divided by 12 is 20 dx dt. Okay. And then we have 1152 divided by 12, which I just did in calculator while you guys weren't looking, and that is 96. Okay. So technically, you don't have, if you're going to be doing the characteristic equation, you don't have to put it in standard form, but it just makes applying the what's it called? The quadratic equation just a little bit easier to do. Okay. Okay. All right. So let's go ahead and form our characteristic equations. We have lambda squared plus 20 lambda plus 96 is equal to 0. Okay. Let's go and find the roots of this characteristic equation. So we have lambda 1, lambda 2 is equal to minus 20 plus or minus, okay, 20 squared minus 4 times 96. Okay. All divided by 2. Okay. All right, so we do this out. We have minus 20 divided by 2 plus or minus square root. Okay. 20 squared is 400. 4 times 96 is whatever 400 minus 16 is, so that's 384. Okay. So that's square root of 16 divided by 2. Okay. And so we get that this is minus 10 plus or minus 2. That means our two roots are minus 8 and minus 12. Okay. All right, so let's go ahead and plug that into our general solutions. We have x of t is equal to c1 e to the minus 8t plus c2 e to the minus 12t. Okay. All right, any questions on how we got that result there? Okay, good. All right, so now that we have our general solution, we can characterize it, okay? So this is a situation where we have two real roots, right? We have two paying exponentials in our solution with different rates. And so this is a situation where we have overdamping. Okay. Now, when I ask you guys to characterize the solution, this is all that you have to do. So you just have to look at your solution, just label it, overdamping, critically damped, or underdamping. Okay. But another interesting thing you can do is you can see how overdamped it actually is. Okay. And the way that you kind of determine that is you can kind of look and see how close your two roots are to each other. Because what tends to happen is that, as you add more and more damping to the system, these two roots tend to kind of go further and further apart, right? So in this case, we have -8 and -12. So it's, it is overdamped, but it's not, okay, it is pretty overdamped. So, you have a difference of 4 here, right? Right. And so if we were to plot this solution, like we mentioned before, if you were to kind of plot out what the solution looks like, the second term or the second solution here is effectively going to be invisible because that one decays down very, very quickly. So the only one that you actually see is C1e to the -8t, right? And so if you wanted to, if you wanted the suspension to be a little bit more, you know, sporty, I guess you can say, where the damping is happens very, very quickly, then you can maybe try to release some of the damping a little bit and kind of bring these roots closer together. Okay. So that's usually what you do, when you want your ride to be a bit more fun, I guess, to be a bit more sporty, is you kind of release some of the damping, you get closer to critically damping so that, your car is very kind of responsive. But, if you want a more comfy ride, you want to, you drive over a speed bump, you want it to feel like a pillow, right? You kind of just crank up the damping and then, you get this kind of over damped solution. Okay. So again, that whole part down there is optional. I don't expect you guys to write that, but just that since we're talking about car suspension, I thought I'd just mention that. Since we're okay. Okay. Any questions on that part there? Okay. All right. So the last thing that we're going to do is we're going to solve this for a case where we run over a speed bump. Okay. All right. So the way that we're going to model this is that we're going to provide basically initial conditions to our differential equation and solve for the full solution. Okay. Okay. So when your car runs over a speed bump, essentially, you're providing an impact. The way the car feels it is that it kind of feels like an impact that's happening from the bottom of the car, right? And so usually the best way to model an impact is to apply an initial velocity. Okay. All right, so let's do that. So let's apply our two boundary conditions. So let's say that x of 0, right? So, no matter the situation, if you have a second order differential equation, you have to specify an initial displacement and initial velocity, right? Sometimes you could have both. Sometimes you could have, a non-zero initial displacement and a non-zero velocity. But, oftentimes, the key to modeling physical situations is to see, what tools or, what numbers kind of best make sense for this situation. Okay. So if we're running over a speed bump, your car is kind of, just kind of riding on level ground right before the speed bump. And so I would make the argument that, your initial displacement before you hit the speed bump is going to be 0. Okay. So we're going to say suspension in equilibrium position right before speed bump. But striking the speed bump is going to give it's going to give your wheel an upward velocity, right? And so we can say dx dt at x equal to 0. So the number doesn't matter too much here. I'm just going to put one that that is convenient. And so we'll say that the speed bump is going to provide an initial velocity on your car's wheel of 10 feet per second in the upward direction. Okay. All right, so we have our two initial conditions. We have our general solution here, right? So even though, I know I said the C2 term, we don't observe it, we still have to solve for it, okay? So let's use these two initial conditions and solve for C1, C2. Okay? All right, first one we have is x of 0 is equal to 0, okay? And so we plug in t is equal to 0 in our solution here. We have C1 plus C2. Okay? Obviously, that's not enough to solve for the equation, so let's go ahead and apply our other initial condition. Okay? So we plug in dx dt at t is equal to 0. Sorry, I put x again. Okay, and so this is minus 8 times C1 minus 12 C2. Okay. So we have these two equations for our two unknowns, right? So you have 0 is equal to C1 plus C2, and then 10 is equal to minus 8 C1 minus 12 C2. So we can solve these two simultaneously to get the values of C1, C2. All right, so I'll kind of leave that for you guys to kind of verify on your own. But what we get from this is C1 is equal to 5 over 2, and C2 is equal to minus 5 over 2. All right, and so our final step here is just to plug in the values of those constants, right? And so our final solution here, x of t is equal to 5 over 2 e to the minus 8t minus 5 over 2 e to the minus 12t. All right. Any questions on how we got that result there?
So this equation will only be true in the case that the speed going up is 10
Exactly.
feet per second.
Exactly. Yeah. Right. So if we can solve this equation for other speeds, of course. So we kind of just put 10 arbitrarily just to have something there. There are better ways to solve these types of equations because who's to say that you run over a speed bump and the speed coming up is exactly going to be 10, right? And so in reality, we can model that as actually an impact, but we need different mathematical tools to actually solve it. So the subject we're going to cover after this is going to be Laplace transforms. And you're going to see Laplace transforms is going to give us the ability to model different types of loading. And so we'll go over impact loading, which is essentially this, and we'll go over step loading as well. Yeah, but that'll be probably a couple weeks, not next week, probably the week after.
And that's also given legal constraints are followed, right? Like if you're going at a certain speed limit, this is true. Otherwise, deviates a little bit.
Right, exactly. Yeah. So if you're going at different speeds, then that's going to affect how much impact is going to feel too. Yeah. When I was in college, I had a friend. She wanted to show off her parents' BMW, so she drove us in the car. She was driving much faster than she probably should have. She ran over a speed bump and she just blew out the complete bottom side of that car. Yeah, and we got to watch her get chewed out by her parents. It was amazing, but yeah, probably not amazing for her, but it was fun to see. It was not so good for me because only a few people could fit in the tow truck, and I lost the bet, and so I had to walk back from the parking lot where we were having fun back to their house, which was like 3 miles. Yeah, I was not happy with it, but I didn't want to chew her out in front of her parents that were already chewing her out. So, all right, any other questions on this result here? Okay. All right, so for the last, I would say maybe 25 minutes of class today, let's start our discussion of non-homogeneous second order ODEs. Okay. All right, so up until this point, we've done a pretty thorough job, examining second order ODEs, right? So we've gone through our 3 different cases, but those have all been for homogeneous solutions. Okay. Right, so I'm going to go back to kind of the notation that we had for generic second order ODEs. So we're going to drop kind of the pretense of mass spring dampers, but just know that all this applies to mass spring dampers as well. Okay. All right. So you have d squared y dx squared plus p dy dx plus qy. Okay. Right, so we have our second order ordinary differential equation. We have our constant coefficients P and Q, right? So far, we've only looked at situations where the right-hand side of this equation was 0, okay? Now, that's great for situations that don't have any external loading, but that kind of limits the class of problems that we can actually examine, okay? So now what we're going to do is we're going to look at situations where this right-hand side is actually non-zero, okay? Right? So our right-hand side is going to be some function of x, right? So this function of x here, we often call the inhomogeneous term or the non-homogeneous term. Right? That's kind of the mathematical name for that term. So probably, when you took 250B, that's what they called it. Okay. But when you're applying this to engineering applications to physical systems, right? That term usually has a very kind of specific purpose. And I think I mentioned this, last time as well, right? We often call this the forcing term. Or I guess to be even more explicit, this is the external forcing term. So basically, if you have any kind of physical system and you have some kind of external force that's continuously going to be, affecting the result of your dependent variable, oftentimes it's modeled with that non-homogeneous term. Okay, so the addition of this term here is going to change our solution, right? So, obviously our solution is going to be different than our previous one, okay? But there's actually a very interesting observation, born from the fact that, these equations are all linear. So the solution to a non-homogeneous second order ordinary differential equation, right, can actually be formed as a summation of two different types of solutions. Okay. All right, and so what we can say is that the solution y of x is equal to, okay, we have the first part of the solution here, which we call yh of x, okay, and we have another part of the solution which we call yp of x. So that yh of x, that h there stands for homogeneous. And so this yh here is the homogeneous part of the solution. And this yp here, we often call this the particular solution to the non-homogeneous part. Okay. All right. So this is actually quite clever, right? Because this kind of leverages kind of what we've done before. So the homogeneous solution, we've actually done this already, right? So this part we already know because this just basically is the solution to what we have been doing. Okay. So to find the homogeneous solution, all we have to do, right, is just set the non-homogeneous part equal to 0 and then solve the corresponding equation. And this utilizes, of course, our characteristic polynomial that we've been doing for the last class and a half. Okay. Good, done. Okay. And so what we're going to focus on, in this part, for the rest of the class today and then on Thursday, is the particular solution. Okay. Now, like I mentioned before, there's lots of different techniques out there to solve for the particular solution. I think at the very least, I think you guys learned either undetermined coefficients or variation of parameters. So we're only going to focus on one method. I think the one that's a little bit easier to implement. And so we're only going to focus on undetermined coefficients. Okay. So that's what I'm going to go over, but just know that if you're more comfortable solving for the particular solution in another way, so you learned it a different way in 250G, by all means go for it. Okay. A couple people have asked me that kind of the way that I've been kind of teaching these things, probably might be a little bit different than how you've learned it previously. If you have another way to kind of solve these differential equations, you use a different technique that you learned. It's fine by me, right? And so I'm going over this stuff just because this is at least to me this is kind of how I typically solve these problems. But I know this is not the only way to solve these types of problems. And so definitely feel free to use whichever method that you want. But just for the class, I'll just be going over undetermined coefficients. Okay. Any questions on this so far? Okay. Okay, so let's introduce the concept of undetermined coefficients, and I think we'll do most of it the next. Okay. So the whole idea with undetermined coefficients, and it's not really there's probably a proof for it. And it definitely has to do with the fact that we have linear equations with constant coefficients. But the whole idea with undetermined coefficients is to look at the functional form of our non-homogeneous term. And we'll go over, the types of functional forms that are common. Okay. And so the whole idea with undetermined coefficients is to say that, if our non-homogeneous term takes a certain form, then our particular solution probably is going to have the same. Right. So that's kind of the best I can do with just kind of a very quick, simple, concise definition without, getting into the proofs and the dirty stuff. Okay. Okay. All right. So what are some common functional forms that we see? Okay. Now, of course, obviously this technique has its limitations. So, we're going to go over some common functional forms that you might see typically in engineering applications. But these are not the only functions that you can do. And so if you have a functional form that's either a very weird combination of these functions or a function that's not here, then you just can't use undetermined coefficients. Okay. But at least the common ones that you see. Okay. You'll often see exponential terms. Okay. You'll see polynomial terms. And very commonly, you'll see sinusoid. So that's sines and cosine. Or often the case, you'll find some kind of sum or product or combination of these function forms. Okay, so once we've identified the functional form of our non-homogeneous term, the idea here is to guess the form of our particular solution to take the same form, but with undetermined or unknown coefficients in front of each of the functional values. All right, and then how are we going to solve for those unknown coefficients? Well, we're going to do the thing that we always do when we have these solutions to differential equations. We're just going to plug it in. Okay. All right, so that's essentially what undetermined coefficients is. And so, I think the only thing to do now is just to kind of do some examples so you can see it in action. Because it's one of those things that it's a very simple concept, but the devil is kind of in the details and stuff. We'll be doing a few examples. We'll probably get through at least one today, and we'll do at least a couple more on Thursday, so you can kind of see the whole process. Because there are a lot of nuances. There's a lot of kind of special cases that I want to make sure that you guys are. Okay. All right, but any questions on this before we get started? Okay. All right. So let's do an example. Okay, so we'll start pretty easy here. All right, so let's say we have this differential equation, d squared y dx squared plus y is equal to 0.001 x squared. Okay. So you can see we have a second order ordinary differential equation, and it's non-homogeneous because we have the 0.001 x squared. Okay. All right, so for this problem, let's solve for the general solution because I don't think I give you boundary conditions. Yes. Okay. All right, so with this example, we'll kind of walk through every step of the process. Okay, so step one, right? For any second order ordinary differential equation that you come across, whether it be homogeneous, non-homogeneous, the first step is always going to be to solve the homogeneous problem. Okay. So the homogeneous problem in this case is d squared y dx squared plus y is equal to 0. Okay. So you basically take your original differential equation and you zero out or you cancel out the non-homogeneous term. Okay. Okay. All right, so just like we usually do, let's go ahead and form our characteristic polynomial. And so in this case, we don't have a first order term, and so our characteristic polynomial is lambda squared plus 1 is equal to 0. Okay. We find the roots of this equation, right? This one's pretty simple. We don't need the quadratic equation. So we get that lambda is equal to plus or minus I. Okay. So we just subtract 1 on both sides. You take the square root. You can't take the square root of a negative number, and so that's going to be an imaginary number. Okay. So from this, we get that YH of X is equal to C1 cosine of X plus C2 sine of X. Okay, pretty straightforward homogeneous problem. Okay. Step 2. Right. Step 2 in these types of problems is to guess a form for the particular solution based on the form of the non-homogeneous term. All right. So for this particular example, our non-homogeneous term, R of X, is equal to 0.001 X squared. All right, so this one's pretty straightforward. So we have basically X squared. And so this tells us that our non-homogeneous term is a quadratic polynomial. Okay, so that means our particular solution is also going to be a quadratic polynomial. Okay. Now, polynomials are interesting because, it's tempting to just say that, our non-homogeneous term just has x squared, and so our yp should also only have x squared, right? But polynomials have to always be complete. If you're forming just a generic polynomial of the second order, you have to include all terms leading up to that second order. Because oftentimes the case that, all those terms that are leading up to it, they're going to have non-zero coefficient values. Okay. Okay, so how do we form this? So that means yp of x, okay, it's actually going to have three terms in it, right? So we need one term for the quadratic, and then everything below that. So we're going to have a quadratic term, a linear term, and a constant term. Okay. Okay, so that's going to be k0. That's going to be our linear term plus k1x, or k0, that's our constant term, excuse me. K1x, that's our linear term. And then k2x squared. Okay. All right, so based on our non-homogeneous term, we have this guess for our particular solution. Okay. All right, any questions on anything so far? How we got this guess here? Okay, and so the final step in this process is to take your guess, take its derivatives, and then plug it back into our original differential equation with the non-homogeneous term. Okay. Okay, so our original differential equation was the following. So we have d squared y dx squared plus y is equal to 0.001 x squared. Okay. All right, so basically everywhere that we see y, we're going to plug in our guess for yp, right? And then if we kind of do our arithmetic, we kind of do everything out, then that's going to give us the equations that we need to solve for k0, k1, k2. Okay? Because those are the unknowns at this point. So these we need to determine what these are. Okay. Okay, so let's go ahead and plug it in. Okay. So first we have d squared y dx squared. So for a simple polynomial like this, we can kind of just do it by, just by looking at it, right? And so we take the second derivative of yp. We know that the constant term is going to go away, the linear term is going to go away, and all we're left with is 2k2 plus y. So for y, we're just going to plug in yp. So that's going to be plus k0 plus k1x plus k2 x squared. And all this is equal to 0.001 x squared. Okay. All right. And so what you're going to do from here is you're going to group the like terms. So you're going to group the terms in terms of, their powers of x, right? So we're going to group the constant terms together. We're going to group the linear terms together. We're going to group the quadratic terms together. Okay. Okay, so first we have the constant terms. So we have 2k2 plus k0. Okay. So these are all the constants. Okay. Plus We only have one linear term, so that's K1 times X. Okay. And we only have one quadratic term, so that's K2 times X squared. And all that is equal to 0.001 squared. Okay. Okay. All right, and so from here, after we've grouped the like terms, we're going to form a system of equations based on these groupings to solve for the coefficients. Okay. So we're basically going to equate, the terms on the left-hand side to what's on the right-hand side. Okay. So I'm going to make the same groupings here. So I'm going to have an equation for the constants, an equation for the linear term, an equation for the quadratic term. Okay. Okay, so let's start with the quadratic term because that one is the most obvious, right? Because that's the only one that we have a non-zero term on the right-hand side. Okay. So for the quadratic term on the left-hand side, we just have K2. Okay. And on the right-hand side, we have 0.001. Okay. So right away, we can see that in order for these solutions to be the same, K2 must be 0.001. So that's good. Okay. All right. So let's look at the linear term now. So for the linear term, on the left-hand side, we have K1. Okay. But on the right-hand side, we don't have any linear term at all. And so, we're going to set this equal to 0. So that again, right away, we can solve for the value of one of our coefficients, K1. All right, and then finally, we have our constant term. So for the constant terms on the left, we have 2K2 plus K0, okay? And on the right-hand side, we don't have a constant term there, so that's equal to 0, okay? Okay, so for this case, we can plug this in just like that, right? So we know K2 already. K2 is 0.001. And so from this, we get K0 is equal to minus 0.002. Okay. Okay, and so we plug those in. We finally get our solution for YP. Okay. So YP of X is 0.001 X squared minus 0.002. Okay. Okay. All right, so that's all the time we have for today. And so, the last thing, well, there's one more step in this problem technically. You can just add this together to the homogeneous solution. But we'll go over that more next time. So when we come back on Thursday, we'll talk about, all the different functional forms that you can have for undetermined coefficients, what your guess for YP should look like. And then we'll do a few more examples to cover some more, I would say more interesting cases. Okay. All right, so thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you all on Thursday. Thanks, guys.
When does this ramp up? And then we hit this, and I said, oh yeah, this is where.
Yeah, these problems get pretty long with the undetermined coefficients. Yeah. Yeah, homework 2 is definitely a step up from homework 1. So.
Yeah.
By the way, I haven't had a chance to check the negative thing on homework 1 yet. Just the weekend was just kind of crazy.
Okay.
But I think you guys are right. But I think a few people have kind of come up with that.
I just did it anyways. So.
Yeah, so when I grade the homeworks, I'll correct that, so that I don't mark people wrong.
Yeah.
Yeah.
Okay. Also, I had a question for you. I got in touch with Edgar. We
Okay.
should be meeting tomorrow.
Okay, perfect.
You said, what was one of the reasons like they didn't approve that project specifically?
They did not approve it, they're not seniors yet.
It's just not, sorry.
It's not seniors yet. And
Seniors
so,
for it, yeah, okay.
so, you know, they're proposing that project to do for senior design, but they're not seniors yet, so they
Makes
can't.
sense.
You know, so I told them to keep it in mind and keep working on it, and then when they're seniors, you know, approach the department and then, you know, see if they can.
Okay, got it. If I have a connection that he works specifically in a part of a company to fund STEM projects, but
Okay,
they require proposals for that. And
Okay.
I don't know how that would work if it's not a senior project, how we would come up with a proposal but still be under CSU.
probably in that case, you'd be under the, I mean, whoever funds it, typically they're gonna take ownership of it. So if you're gonna find funding outside, that's perfect. Then you're kind of free from CSUF as a bond.
Oversight. Okay.
Yeah.
Okay.
Exactly. Yeah, I mean, judging, I mean, he didn't tell me all the details of what he was proposing, but that may be a better route, just so you have more, you're probably gonna get more resources and less restrictions then.
Yeah, I guess the way, maybe I gotta clarify, but the way it sounded was, hey, write your proposal for CSUF, and as long as we see that,
Yeah,
we can provide whatever tools you need for the.
Yeah.
project.
so if you guys go that route, then, you know, there's gonna be a separate process if you guys wanna do that for senior design, but if you do that, then the project may be done before you even get to seniors.
That's the idea.
So that's but then you'd have to do something else. For senior
Oh, yeah,
design.
oh, yes, okay, gotcha.
But I think probably that might, just because it seems like when I talked to Edgar, his idea is already pretty mature.
Mhm.
And so that might be the better route, but he's not waiting until senior design to really kind of put that into motion.
Yeah.
If there's a way where he can get the resources now, that might be what he does. So,
I'll talk to him then.
Sounds good.
Just want to talk to you.
Yep. Mhm.
Thank you.
Yep. Thanks.
I just wanted to check if we know how to use like annihilators and some of these things.
Yeah, of course. Yeah, any method that you can have. So I'm only going over this just because that's all we have time for.
Yeah.
But you know, feel free to use whatever method you learned previously. So, yeah.
About the real example?
Yep.
Where did you get 5-2 from?
So we basically solve these two. So I kind of skipped that step just because of time. But we basically solve these two equations at the same time to get 5/2. So basically from this first equation, you see that C1, C2, they have to be same magnitude but opposite signs. You just plug it back into this one down here.
So that would be
So let's see. So we see that we solve for C1. So C1 is equal to minus C2. And so we get 8.
minus 12. Right?
Yes. So 8, positive 8 minus 12, that's minus 4 divided by 10. Or no, 10 divided by minus 4. So that's minus 5/2 for C2.
So it's 10, and then this is minus C2, right?
Minus 4 C2.
And the 4 came from just taking away the C1.
Yeah, so the C1 basically we plugged in from the first equation. So we know that C1 has to equal minus C2, right? So minus C2 on both sides.
Oh, okay.
Yeah,
I see it.
and we plug in.
Okay.
Yep.
And then, okay.
Yep.
Okay. Cool. Thank you.
Yep. Mhm.